In this video, we're going to continue talking about summarizing bivariate data, but we're going to be talking about linear regression and fitting a line to bivariate data. So, what is the object of regression analysis? Well, suppose that we have two variables, and x equals the amount spent on advertising, and y is the amount of sales for the product during a given period. Well, what question might I want to answer using this data? The object of regression analysis is to use information about one variable, the x, to draw some sort of a conclusion about a second variable, or y. So our x variable is the independent or the explanatory variable, and our y variable is the dependent or response variable. We will use values of x to predict values of y. Now, scatter plots frequently exhibit a linear pattern. When this is the case, it makes sense to summarize the relationship between the variables by finding a line that is as close as possible to the plots in the point. The plots in the plot itself. Now, this is done by calculating the line of best fit, or the least squares regression line, the LSRL. Now, the LSRL is y hat equals a plus bx. Again, that's y hat. It means the predicted y. Make sure you put the hat on that y. Now, b is our slope. So that's our approximate amount by which y increases when x increases by 1 unit. And a is the y-intercept. It is appropriate, or it's approximately the height of the line when x equals 0. Now, in some situations, the y-intercept has no meaning. Now, the equation for finding the slope of our LSRL is this equation right here. So we'll be summing the deviations of x times the deviation of y divided by the sum of the deviations of x squared. Now, the intercept of the LSRL is a equals y bar minus b times x bar. The LSRL is the line that minimizes the sum of the squares of the deviations from the line. Let's explore what this means. Now, suppose we have a data set that consists of the observation points 0, 0, 3, 10, and 6, 2. Let's just fit a line to the data by drawing a line through what appears to be the middle of the points. So here we have that y hat equals 0.5x plus 4. Now, we're going to find the vertical distance from each point to the line. So we'll do that for our 0, 0 by plugging in 0. We plug that in, we see that we have a y value of negative 4 because we're down 4 for our point. Then here we'll plug in our 3, and we'll plug that in, and we see they're going to have 4.5. Then for 6, 2, we'll plug in a 6, and we see that we'll get a negative 5. So I want you to find the sum of the squares of these deviations. The sum of the squares is 61.25. So we're going to use a calculator to find the line of best fit here. So what that means is you're going to be going into your y equals, or really not your y equals, more of into your stat list, and you're going to put these variables, or these data points, into your list. Then you're going to go to stat again and to calculate. So here we have our list set. So we'll come over to stat and we'll go over to calculate. And we're going to come down here to our linear regression, but we're going to choose option 8. Notice that this time it says a plus bx. So we're not going to choose option 4 because that's the wrong kind of linear regression. So we want our a plus bx. And we're going to go ahead and we're going to hit enter. We're using our lists, and it's going to calculate our correlation coefficient as well. And so here we see that we're going to have an a plus 1/3 x. for our equation of our line. So now we're going to take that and we're going to put it into our y equals. So we're going to have our a, which is 3, plus our 1/3. So 1/3 x. And now we're ready to graph this. So now when we've graphed that, we have y hat equals 1/3 x plus 3. So we're going to find the vertical deviations now from this line. So here we'll find it, a value of -3. When we plug in our 3, we'll get a value of 6. When we plug in 6, we get a value of -3. Now, what is the sum of the deviations from the line? It's 0. Well, will it always be 0? We want to find the sum of the squares of the deviations from the line. So go ahead and do that really quick. And push pause, and when you're done, push play, and we'll see if you're right. So you should have gotten that the sum of the squares was 54. Now, this is the line that minimizes the sum of the squares of the deviations from the line, which is our LSRL, or least squares line. So let's go ahead and let's do some more examples. So here, researchers are studying pomegranates' antioxidants properties to see if they might be helpful in the treatment of cancer. So in one study, mice were injected with cancer cells and randomly assigned to one of 3 groups: plain water, water supplemented with 0.1% pomegranate fruit extract, or PFE, and water supplemented with 0.2% PFE. Now, the average tumor volume for mice in each group was recorded for several points in time. So X is going to be the number of days after injection of cancer cells in mice assigned to plain water, and Y is going to equal the average tumor volume in millimeters cubed. So here's our data plot. So we're going to sketch a scatter plot for this data set. So I'm going to go ahead and have you do that. So I want you to push pause and put that into your calculator and go ahead and make a stat plot for that. So our stat plot should look something like this. So now I want you to calculate the LSRL and the correlation coefficient. So push pause and then go ahead and do that. Go to your stat menu and go to calculate and do that. And when you're done, write it down and then push play and let's see if you're right. So you should have gotten y hat equals -269.75 plus 37.25x, where r had a value of 0.998. So here we see a really strong correlation, right? So we want to interpret the slope and the correlation coefficient in the context. So that's telling us that the average volume of the tumor increases by approximately 37.25 millimeters cubed for each day's increase in the number of days after the injection. Now remember that an interpretation is stating the definition in context. There's a strong, positive, linear relationship between the average tumor volume and the number of days since injection. Does the intercept have any meaning in this context? Why or why not? The answer would be no. With what we're talking about, having that negative number is impossible. You can't have negative cancer cells or a negative volume. So we're going to go ahead now. We're going to predict the average volume of the tumor for 20 days after an injection. So we're going to take that 20, we're going to plug it in, and we're going to get 475.25 millimeters cubed. Now, let's predict the average volume of the tumor for 5 days after injection. So I'm going to let you go ahead and do this. So go ahead and push pause and do it. When you're done, push play and let's see if you were right. So So you should have gotten an answer of negative 83.5 millimeters cubed. But can volume be negative? No. This is the danger of extrapolation. The least squares line should not be used to make predictions for y using x values outside of the range of the data set. Why not? Because it's unknown whether the pattern observed in the scatter plot continues outside of the range of x values that we were given. Now, suppose we want to know how many days after injection of cancer cells would the average tumor size be 500 millimeters cubed. So solve for x, right? So we want to know, is this the appropriate regression line to answer this question? And the answer here is no. The slope of the line for predicting x is r is s sub x over s sub y, which is not r times s sub y over s sub x. And the intercepts are almost always different. Here is the appropriate regression line for this. X hat equals 7.277 plus 0.027y. And in case you forgot, the s sub x and the x sub y are denoting the sample standard deviations of the x's and the y's. Oops, let's go back for a second. Now the regression line of y on x should not be used to predict x, because it is not the line that minimizes the sum of the squared deviations in the x direction. Let's go back. So let's talk about finding the mean. So I want you to find the mean of the x values and find the mean of the y values. So go ahead and push pause and go ahead and do that. And when you're done, push play and we'll check and see if you're right. So you should have gotten an x mean of 19 and a y mean of 438. So now we want to plot the point of averages on our scatter plot. And you can do that by taking your calculator and adding that point to your list. Notice where that ends up. The point of averages is always on the regression line. So now, go ahead and take out your point of averages from your list and sketch a scatter plot. Notice our values have changed. So we're going to investigate how the LSRL and the correlation coefficient change when different points are added to the data set. So go ahead and put those values in, sketch the scatter plot, calculate the LSRL and the correlation coefficient. Push pause, and then when you're done, push play and we'll see if you were right. So for your y hat, you should have gotten a negative 3.8 plus 1.5x with a correlation coefficient of 0.916. So showing a strong correlation. So suppose we added the 0.5, 8 to the data set. What do you think is going to happen to the regression line and to the correlation coefficient if we do that? So I want you to go ahead, go into your stat plot, or not your stat plot, but into your list, add the 0.58, and then recalculate your LSRL, your correlation coefficient, and replot your scatter plot. Push pause, and when you're done, push play, and we'll see if you're right. So here, you should have seen that you got a y hat of negative 1.15 plus 1.17x with a correlation coefficient of 0.667. And what happened? Well, our LSRL is now not quite as strong. Our relationship is moderate because we went from a 0.916 to a 0.667. Well, suppose we added the point 1212 to the data set. What happens to the regression line and to the correlation coefficient here? So go back in and take off those last 2 points we put in, and now put in 1212. Push pause, and when you're done, push play and let's see if you're right. So here you'll see that now your y hat is negative 2.24 plus 1.225x, and our correlation coefficient is 0.959. So it has increased the strength of our relationship. Notice that our point is closer to that line of best fit. Let's make one more adjustment. So let's go ahead and let's add the point 2, 0. So go back into your list, take off 1212, put in 12, 0 to the data set, then calculate the regression line and the correlation coefficient. And let's see what happens. So push pause, and then when you're done, push play, and we'll see if you're right. So you should have gotten a y hat value of 6.26 minus 0.275x, and your correlation coefficient is now negative 0.248. You can see from your scatter plot that our point is way down here, and our line is like a mess. It's going to negative now. It's crazy, right? So simply adding these extreme points on makes a difference. And so it's important to know that the correlation coefficient and the least squares regression line are both measures that are affected by extreme values.